my dear students. Today we will continue with the lesson electric resistance and Ohm's law. So today we will start with Ohm's law. The Ohm's law in vector form. Okay. So the relationship between the current and the voltage in macroscopic form is represented by Ohm's law in terms of electric field and current density. Okay. So we have the formula for the potential difference. We have to write out the formula for the potential difference in terms of the m v equal to m upon n e square tau l upon a into I. So this is a relation that we had derived. V equal to m upon n e square tau l upon a into I, where m is the mass, n is number of electrons, e is the charge on electron, tau is the relaxation time, L is the length of the wire, A area of cross section of wire, and current. Now we bring L here, V upon L equal to m upon n e square tau I upon A. Okay, V upon L, this is electric field. V upon L is electric field. So V upon L is equal to E, and m upon n e square tau is the specific resistivity. This we had discussed in the last video. And I upon A is current density, represented by the letter J. So we substitute these values. V upon L की जगह क्या आ गया E, m upon n e square tau की जगह क्या आ गया rho, and I upon A की जगह क्या आ गया J. Now what relation are we getting? We are getting a relationship between the electric field and the current density. Electric field is equal to rho J. Rho is specific resistivity of the wire or the material. So E equal to rho J, or E equal to 1 upon sigma J, where sigma is specific conductivity. So inverse of specific resistivity is specific conductivity, represented by the letter sigma. So E equal to 1 upon sigma J, or J is equal to sigma E. J equal to sigma E, where sigma is constant. We know that specific resistance or specific conductivity is the property of the material, so which is a constant value. So J is directly proportional to E. J, the current density is directly proportional to E. Thus, Ohm's law in vector form. This is Ohm's law. J equal to sigma E. This is the representation of Ohm's law in vector form, or J is directly proportional to E. Thus, Ohm's law in vector form states that current density is directly proportional to the electric field applied across the end of the conductor. Okay, and the direction of the J, since both J and E are vector quantities, so direction of J coincides with E, or more specifically, the law states that the ratio of the current density to electric field is constant, which is independent of the electric field producing the current. Dependence of resistance on the dimensions of the conductor. Now we have resistance. Resistance is given by the expression m upon n e square tau l upon a, and these values, m mass of the charge, n number of electrons, e the charge of the electron, tau the relaxation time, all of them are constant value. So m upon n e square tau is represented by this rho, which is specific resistance. What is it? Specific resistance, which depends upon the material. So instead of all these we put rho. Now what do we get? R is directly proportional to L upon A. That means resistance is directly proportional to length and inversely proportional to area of cross section. Okay, resistance is directly proportional to the length of the conductor. More the length of the conductor, more is the resistance, and inversely proportional to the area of cross section. More the area of cross section, जितना मोटा तार होगा resistance उतना कम होगा. जितना पतला तार होगा, जितना कम उसका डायमीटर होगा या जितना कम उसका एरिया ऑफ क्रॉस सेक्शन होगा, उतना ज़्यादा उसका रेजिस्टेंस होगा, इट इज इनवर्सली. So if area of cross section is more, resistance is less. If area of cross section is less, resistance is more. If the conductor is remolded to change its length and cross sectional area, then its mass, that is the volume, are assumed to be constant. That is, shape is changed. Whether the wire is stretched or wounded over itself, in that case volume will remain constant. Now we have the formula for the volume. Volume is equal to length into area of cross section. So L1 A1 equal to L2 A2. Now area of cross section is given by pi r square. So L1 pi r1 square, L2 pi r2 square, pi cancel out. So we have a relation L1 r1 square equal to L2 r2 square. Now we have a first case. If the resistance in the initial condition R1 is L1 A1 R1 and in the इसका रिलेशन जो कोई वायर है जिसका लेंथ L1 है, एरिया क्रॉस सेक्शन A1 है और रेडियस R1 है, ओके, उसका रेजिस्टेंस है R1 और उसको हमने क्या किया, खींच के डबल कर दिया. वी हैव इंक्रीज इट्स लेंथ. नाउ द लेंथ इज L2 A2 R2. नाउ by the formula R is directly proportional to L upon A. We have R2 upon R1 equal to L2 A1 upon L1 A2. We substitute the values here. What do we get? We get L2 upon L1 का whole square. For example, another example, if the wire is stretched n times, वायर को खींचे n times कर दिया तो नई लेंथ क्या हो गई, n times the initial length. So L2 will become n times L1. L2 will become n times L1. तो यहाँ पर हम कंडीशन क्या कर रहे हैं, L2 क्या हो गया n times L1. यहाँ पर हम वैल्यू रख देंगे तो R2 upon R1, L2 की जगह क्या गया n L1 upon L1 का होल स्क्वायर इट इज इक्वल टू n times n स्क्वायर. So R2 will become n स्क्वायर टाइम्स R1. तो यहाँ पर मैंने बोला था अगर हम वायर को दुगना कर देते हैं, वायर को L2 को वायर की लेंथ को दुगना कर देते हैं तो रेजिस्टेंस 4 गुना हो जाएगा. तो रेजिस्टेंस विल बिकम 4 टाइम्स. इज इट क्लियर? इफ वी स्ट्रेच द वायर टू ट्वाइस इट्स लेंथ, then the resistance will increase to 4 times. So this is a direct formula for increasing the length. When the length is doubled, the resistance increases to 4 times. Now we have the second case where the area of cross section is changed. We have a change in the area of cross section. Now we have the relation R is inversely proportional to L upon A. So we have R2 upon R1 equal to R2 over L2 upon L1 A1 upon A2. Okay. Now from this formula L1 A1 equal to L2 A2, तो L2 upon A2, L2 upon L1 की वैल्यू क्या हो गई, A2 upon A1. L2 upon L1 की वैल्यू क्या हो गई, L1 की वैल्यू हो गई A1 upon A2. So यहाँ पर हमने L2 upon L1 की जगह रख दिया A1 upon A2. So what do we get? A1 upon A2 का होल स्क्वायर. क्लियर? इस रिलेशन से हमने क्या निकाल लिया, L2 upon L1 का रेशियो. तो L2 upon L1 का रेशियो क्या आ गया, A1 upon A2 मल्टीप्लाई कर दिया A1 upon A2 का होल स्क्वायर. Now A1 is area of cross section. This is pi R1 square upon pi R2 square. So pi से pi कैंसिल हो गया तो R1 square upon R2 square. Now R1 upon R2 का होल की पावर 4. इसका मतलब क्या हो गया, the relationship is resistance R2 upon R1 is equal to R1 upon R2 की पावर 4. R1 upon R2. Now it is inverse. R1 upon R2 की पावर 4. For example, if the wire is stretched, वायर को स्ट्रेच किया, उसका एरिया ऑफ क्रॉस सेक्शन क्या हो गया 1 upon n टाइम्स. Then the resistance R2 upon R1 will become n raised to power 4. if the wire is stretched so that its area of cross section becomes 1 upon n times thinner, 1 बटे n times thinner हो गया, then R2 upon R1 is equal to n raised to power 4. In all these cases, the resistance depends upon length and the area of cross section, but the resistivity is independent of length and area of cross section. So whether we are stretching the wire, we are making this length double, triple, or we are binding over itself, we are increasing the area of cross section, there is no change in the resistivity of the wire. Next topic is effect of temperature on resistivity or resistance of the wire. Now when we talk about metals, so we are talking about the resistivity or the resistance of metal. When the temperature of the metallic wire is increased, its resistance increases. So the resistance of the wire increases with the increasing temperature. That is what we have stated in Ohm's law also. Physical condition remaining the same, temperature remaining the same, then only the current is directly proportional to the potential difference applied across the end of the conductor. So if the temperature increases or temperature changes, then the resistance also changes. Temperature increases with the increase in resistance. We will discuss this. We have from Ohm's law resistance. We have from the Ohm's law for a given wire of length. Suppose the length of the wire is L and area of cross section is A. Then the resistance of the wire is given by the formula R is equal to M N E square tau L upon A. M is the mass. N is number of electrons per unit volume. E is charge. Tau is relaxation time. Now N E square tau L upon A for given mass. For mass is constant, number of electrons per unit volume are constant, charge is constant, and for given length and area of cross section of wire, our resistance is inversely proportional to the relaxation time. R is inversely proportional to relaxation time. Now what is relaxation time? Relaxation time is the average time between two consecutive collisions. ठीक है? तो relaxation time क्या है? It is a time taken between two consecutive collisions of the free electrons with the parent atom. So that is relaxation time depends upon the formula Vrms upon lambda upon Vrms. That is tau depends upon the distance, mean free path upon the velocity Vrms. Okay, root mean square velocity of the electron. So the relaxation time, distance upon speed, distance is mean free path, lambda upon Vrms. We substitute the values, we get resistance is directly proportional to Vrms upon lambda, that is mean free path. Now we know that the root mean square velocity is directly proportional to the absolute temperature. Root mean square velocity is directly proportional to the temperature. As the temperature will increase, the mean free path will decrease, because with rising temperature, the amplitude of the vibration of the positive ions of the metal increases and they further obstruct the path of the free electron. Now what will happen? Vrms is directly proportional to T. Therefore, the resistance becomes directly proportional to square root of temperature. As the temperature increases, the resistance of the wire increases, because we will substitute instead of Vrms root T. So resistance is directly proportional to the absolute temperature. Okay, next formula we have RT equal to R0, RT equal to R0 1 plus alpha T. Okay, where the resistance RT is the resistance of the wire at T temperature, R0 is the temperature resistance of the wire at 0 degree Celsius, alpha is the coefficient. Okay, what is alpha? Alpha is the temperature coefficient of resistance. Alpha is temperature coefficient of the resistance. So at any given temperature we can find out the temperature or the resistance of the wire. RT is equal to R0 1 plus alpha T. And if you have to find out the temperature coefficient of resistance, alpha is equal to RT minus R0 upon R0 into T. Okay, T is the temperature. So unit per degree Celsius. So temperature coefficient of the resistance can be found out by the formula RT minus R0 upon R0 into T per degree Celsius. Or if we take R0 equal to 1 ohm and T equal to 1 ohm, then RT minus R0 is equal to increase in temperature. So what is it? What is RT minus R0? This is increase in the resistance. Increase in resistance upon original resistance into rise in temperature. Okay, that will give you the temperature coefficient of the resistance. So what are we getting here? RT equal to R0. What are we getting? RT equal to R0 1 plus T upon 273. Okay. This is giving you RT is directly proportional to temperature. Okay. So the resistance is directly proportional to the temperature, where T is absolute temperature. So if the temperature will increase, then the resistance will increase. Now we will see the variance of resistivity with the absolute temperature in the case of the metals, alloys and the semiconductors. So these are represented by graphs. Graphs are very important. They are often asked in the examination. So we know that in the case of the resistance or resistivity of metal, resistivity is directly proportional to the absolute temperature. So it will increase with the increase in temperature. Directly proportional means the resistivity will increase with the increase in temperature. This is resistivity. Here this graph is between resistivity and the temperature. Rho is representing resistivity. Okay. Or resistance also, it will remain the same. Resistance will also increase with the increase in temperature because the resistivity is directly proportional to resistance. Okay. Now here, what are we seeing? We are seeing that at 0, the resistivity is not 0. Resistivity is not 0. So if we bring down the temperature to absolute 0, then also the resistance or the resistivity does not become 0. It reaches certain infinite value. Okay. So it will reach a certain infinite value. It will not become 0 even at the absolute 0. Then you can see this portion is not a straight line. The straight line starts from here. This is a straight line here. So there is always a curved non-linear region at very low temperature. So at very low temperature, resistivity for metal is not directly proportional to absolute temperature. So small bit of non-linear region is shown here, where the temperature reaching absolute 0. So it's not a straight line. Afterwards, when the absolute temperature increases, then the resistance of the metal increases in a linear way. It becomes a straight line. Then the next graph is for resistivity of alloys. The resistivity of alloys also increases with the rise in temperature, but this increase is much smaller than the metal. The graph alloys also behaves like metals only, but only thing is that the slope, look at the slope of this graph and this graph, the slope is very less. Okay, the slope of the graph is less. So the resistivity changes very little, very small as compared to that of metals. Okay, in the case of the metals, the resistance varies directly proportional to the temperature and the slope is large. So it rapidly changes, whereas in the case of the alloys such as nichrome, which is an alloy of nickel and chromium, the resistivity increases with the temperature, but this increase is very small. Okay. Nichrome has a large resistivity even at 0 Kelvin. This resistivity is called residual resistivity, and this is used to check the purity of the metal. On account of high and little temperature dependent resistivity, alloys like manganese, constantan, nichrome, etc., they are used to make wires for standard resistance boxes or rheostat. Okay. Since you can see the slope is very small, what does it mean? That with the change in the temperature, there is very small change in the resistance of the alloys. So there is hardly much change in the resistivity of the alloys with the change in temperature. So certain alloys such as nichrome, manganese, constantan, they are used for making resistance wire. Okay. And the third one we have on the side, resistivity of semiconductors. Now if you look at the resistivity of the semiconductor, it's a totally a different kind of graph. Okay. There are certain substances which are known as semiconductors, whose conductivity is lying between metals and non-metals, or good conductors and bad conductors. So there are certain substances whose electrical conductivity is very large compared to insulator but small compared to conductor. These are called semiconductors. Examples: silicon, germanium, selenium, carbon, they are semiconductors. The resistivity of the semiconductor decreases rapidly with the rise in temperature. Okay, as the temperature will increase, the resistivity of the semiconductor will decrease rapidly. That is, their temperature coefficient is negative. Temperature coefficient is negative. At high temperature, they will give you very large current because resistance will be nearly 0. Okay. So the resistivity of the semiconductor is very high at absolute 0. You can see the graph is almost touching the x-axis. So it is almost 0. You don't get current. When the temperature increases, the resistivity decreases. Okay. Therefore, the resistance we have, the reason is that for these substances, N, and what was, we had the formula R is equal to M L N E square tau A. So N is the number of electrons per unit volume. At very low temperature, number of electrons per unit volume is very less. So the value of resistance is very large. But with the rise in temperature, more and more electrons come out in the case of semiconductor, and the resistivity keeps on decreasing. Okay. Although in these substances the relaxation time tau decreases with the rise in temperature, but the increase in the value of N is very large as compared to the decrease in tau. So the resistivity decreases. So you should remember all these three graphs. They are often asked in the examination. So resistivity of metal, a straight line but the slope is large. Resistivity of nichrome, again a straight line but the slope is very small. And resistivity of semiconductor, it's a hyperbola. Resistivity is very large at 0 degree Celsius, 0 Kelvin, and as the temperature increases, the resistivity decreases. Okay, the resistivity decreases. The next thing we have resistivity of electrolytes. The resistivity of electrolyte also decreases with the rise in temperature. The reason is that with the rise in temperature, the viscosity means gadapan, the viscosity of the electrolyte decreases, so that ions get more freedom to move inside the electrolyte. Hence the resistivity of the electrolyte decreases. That is very important. When the temperature increases, the viscosity decreases and the ions become more free to move in the electrolyte. So the resistance decreases. So resistivity of electrolyte decreases with the increase in temperature. Then we have nichrome has high resistivity, low conductivity and a very small temperature coefficient of resistivity. So the resistance is not much affected by the change of temperature. For this reason it is used to make standard resistance. We use copper wires in household electricity for wiring. Reason? Because it has got very high conductivity, 5.8 into 10 raised to power 7 per ohm per meter, and as such copper wires are used in connecting wires. So today we end up the session here only. In the next video we shall be discussing about the color code of carbon resistors and also the combinations of resistances.